In this video, we will explore the second effect generated by special relativity, length contraction. As you may remember, in the previous video we saw that the speed of a moving object will generate two important effects: time dilation and length contraction. But these effects will become apparent only when the speed of the object becomes an important fraction of the speed of light. Length contraction is the shortening of the physical dimensions of an object that moves at a fraction of the speed of light when observed by an observer at rest. In order to make an easy deduction of the length contraction equation, let's think of the following experiment. Suppose that you build a spaceship that is capable to travel at a fraction of the speed of light. Your design determines that the length of the ship is equal to L sub 0. When finished, a mission sends it to the space, and the trip at high speed starts. After accelerating, it reaches a constant speed v. Due to some technical issues, you need to use a telescope to observe the ship from the Earth. You observe that the length doesn't correspond to your original design, then decide to figure out why this is happening. In order to calculate the observed length of the ship, you use your telescope and a timer at your position, and call it delta tau, because you are at rest. Also, you know that in the ship there is another timer, that you call delta t. This is the moving reference system. Finally, you know that in both reference systems, the speed of the ship is simply v. Using the data you have, you can see that. And then, finally, the observed length of the ship is calculated as the original length, L sub 0, divided by gamma. Or, in other terms, it is important to see that, as gamma is always smaller than 1, the observed length, L, is shorter than the original one. This is why this effect is called length contraction. Now, let's solve an example to see how the length contraction equation works. Example 3. Suppose that a train is 100 meters long at rest. Calculate its length measured by a resting observer when the train speed is 0.5 c. Could you solve this example? Answer. We know that the original length is 100 meters. We know that the length contraction equation is, or, in terms of the speed. If we now insert the value of the speed of the train in the equation, we see that, finally, the calculated value is about 86.6 meters. It is clear how, due to the speed is an important fraction of the speed of light, the observed length is reduced by about 15%. As stated before, if we think of the speeds we use in our transportation every day, we see that the relativistic effects, although present, are not apparent to our eyes. With this, we finish the analysis of the direct effects of relativity. In next videos, we will explore the consequences of time dilation and length contraction in the definitions of velocity, momentum, and energy. Stay tuned.